one of the interesting things about LM models is that they don't necessarily interact directly with an environment. It's like that's a big discussion around LM models, right? Like, can they be intelligent without that direct environmental interaction? And then so we know that that doesn't exist. So it's a different framework overall for training an LM model. And so that was kind of a bottleneck for a long time. Is so how do we take this reinforcement learning and actually train an LM model on it? And then so there's in the last like few months or so there's been a lot of breakthroughs around that and a lot of research papers and a lot of advancements like how exactly do we do that. And then so we've kind of decided and we've built out kind of reward functions that we can utilize to train an LM model and have it utilize rewards that aren't environment based, that are more like text based or based off of prompts overall. And then so we can utilize that as the specific reward function within the reinforcement learning training. And then so that's what happens within Deepseek, right? And that's this R1 model is that it's going through that type of training. And then so you can think of it as like it prompting itself, right? So it will go through like a training process and it will be what is the meaning of 42. It's just the first thing that came to my head, you know? And then it will have it, and then through its training, it will reason through that, right? That's kind of the goal is to have it within their specific training functions specifically. They put in these thinking tokens. They introduce it very specifically within this paper, and then so they want to give the model a prompt like what is 42, like something that's open ended, and then they give it these thought tokens, thinking tokens, and then that's what it's utilized. Those thinking tokens are part of the built-in reward function for this model, which is interesting, right? They
That's
do
like super
do
crazy.
interesting things with the reward function on this model specifically. They
Okay.
do it based off of those thinking tokens, and then they do something like they have a reward very specifically for the format of the output, which is interesting, right? So they say they reward the model on like its structure, and then the model is self-rewarding in this instance, right? So it's improving itself as it goes through. But so diving deep into your question, and this is the long way to get into that aha moment, right? Because you have to
Right,
understand
yeah.
first what exactly this training process is. So it's
Right,
literally going through and prompting itself, right?
right.
What is how do you build a house? That would be a good example, right?
Mm-hmm.
And then so maybe it says like it starts off, you build a house by nailing boards and you build a wall, and then but then it would so it goes through, and then part of that process with those thinking tokens, maybe it goes through and it starts generating that, right? Be like, let's build the wall, but then it'll be like, wait a second, the foundation comes before the wall when you build a house. Aha, right? And then so that's that where it will have that chain of thought process where I'm wrong because it's a
That's crazy.
that's a good way to
Yeah.
frame it, right? Like the
Right,
I'm wrong moment in my thought
right,
processes, because with LM models that's like a big thing with them, right? And that's known,
right,
like they won't say when they're wrong, and
right.
so
Yeah.
they're always just confidently incorrect. And then so this
Yeah.
aha moment is an overcoming of that confidently
Oh.
incorrect. Like it's like, aha, I'm wrong. Let me change direction.
Okay, okay, okay. So is that a thing where we use reinforcement learning to achieve that aha moment? Because normally ChatGPT or the models before we used to have, they didn't use reinforcement learning as DeepSeek does, right?
That's correct. Yeah, yeah. So reinforcement learning in this concept, as I've just described it, is a like
Right,
I'll call a brand new concept for LLM models specifically. For LLM models
right.
specifically, you are probably familiar with the concept of RLHF, or
Mm-hmm.
reinforcement learning with human feedback. And then
Right.
so like RLHF is a completely different. They're two different processes than RL. Like RL is all automated, right? It's
Hmm.
just like the model is,
Right,
you're like on a complete treadmill, and it's
right,
like running itself. Is
right.
like kind of the best way that I can put the
Mm-hmm.
difference there. Whereas like RLHF is you're simulating labels. for the
Hmm.
model, whereas with RL, the model itself is simulating the labels. I guess that's a simple
Right. Yeah,
distinction.
that's simple. Yeah, I got that. So, Deep, both things are happening with DeepSeek, right? Or only human feedback thing happening?
Yeah, yes. Yeah, so this reinforcement learning process is like that's the kind of like the foundation of the DeepSeek R1 model. So it's like when they refer to also the aha moment, that's referring to reinforcement learning, as well as like they mention like cold start in this model a lot, and that they skip the SFT process, supervised fine tuning. All of that is referring to the reinforcement learning process, and then kind of
The cold
how
start,
they
right?
there it is cold start yeah, and how
Yeah.
they kind of utilize that framework
Mm.
to train the model very specifically. It's all their methodology within this is all reinforcement learning based. Like so, there's no supervised fine tuning. There's no unsupervised learning. It's all just straight RL, right?
Right, Arvin. Yeah.
Pretty amazing, right? Like
Yeah,
and
that's super awesome.
it's intriguing to me because the model is self-correcting. It is actually learning in that instance, right?
Right. So, what's the reasoning ability like? What's rejection sampling and supervised fine tuning in this paper? Was
Yeah.
yeah,
So this is like the big thing that it's coming out of this, right? Like this, I'm
right,
glad that you point this out. So this rejection
right.
sampling and supervised fine tuning and that they're not utilizing those methods overall, right? That essentially,
Hmm.
uh, unlike cold start methods, they're utilizing pure reinforcement learning, and then so it's
Exactly
just like
right.
this. Playground, right? Like it's kind of like the bottom line. Like you give the model a playground environment, you allow it freedom to like generalize in some instances. It's kind of like
Mhm.
the most simplistic way that I can put it.
Right,
And the model has better outputs and better rewards, results and better rewards.
right,
And I think
right.
I would base it all off of that. I think like why does this work scientifically,
Mm-hmm.
and boiling it down to that, I think it comes
Mm-hmm.
down to that. And you'll see like there's a lot of discussion
Mm-hmm.
that people have around gradient descent, right? So
Right, yeah.
typically when we train a model via supervised fine tuning or unsupervised learning, etc., I'm utilizing gradient descent as like
Right.
the reward, like how I'm
Completely.
tuning it, right?
Right.
Which is not it's known that that's not the best reward function, but I don't know what a
Mm-hmm.
better reward function would be. Whereas
Right.
with this reinforcement learning, like kind of one of the unique things about it is the
Mm.
model is designing its own reward function as it goes through.
Right.
So
That's really crazy.
inherently, it's
So,
improving off of that gradient descent function, which
right.
is a like significant improvement in and of itself. So I would say that a lot of these improvements
Mm-hmm.
likely boil down to that. Like I would explore that as an area further within this.
Completely, yeah. So, what they mean when they're comparing distillation with reinforcement learning?
Yeah, absolutely. So distillation is a fantastic and a unique concept to me overall, right? I mean,
Mm-hmm.
like the first time that I heard like distillation and that you can actually do this, it blew my mind
Right.
as to what you actually do, and it's very straightforward what you do, right? So let's say
Right.
I take a data set and I take
Mm-hmm.
a math data set, right?
Okay.
And I take a model, a cold model, like a let's say a BERT model, and it's
Mm-hmm.
untrained, so there's no like nothing. It knows absolutely nothing, right? And then I train
Right.
it on this math data set. Now, let's say I train
Mm-hmm.
it for like 6 hours, and it's a big data set. I get like a
Right.
good amount of training, and then
Mm-hmm.
uh, the result of that training is that the model updates its weights at the end, right? And then
Right.
it like I don't know, it updates its weights too, but it updates its weights based off of this training. And then so
Completely.
let's say like I'll 1.0, 0.5, zero point 0.8, and zero point 0.4. Right?
Mm-hmm.
And those are the pretend weights that it updates to at the end, right? I can
Right.
just take that, like those weights,
Mm.
the 1.0, the zero point 0.5, the zero point 0.4, and the zero point
Mm.
0.8, and I can just take that in and of itself, and those weights, I distill the weights, and I take those weights, and then I take a new BERT model, and I just give it the weights. I don't give it the data. I don't give it anything else. I'm just like, here's the weights, the 1.0, the zero point 0.5, the zero point 0.8, and the zero point 0.4, and I plug those in, and then I test that model on the math data set. It will do better than the teacher in some instances, and
Completely,
that's what
yeah,
their
that's
method here
crazy.
is showing, right? That
Right.
so I train the teacher to,
Mm-hmm.
let's say, 80% accuracy, and then I
Hmm.
take its weights and I distill it, and I take
Hmm.
it to a smaller model, even into a student model, and I put
Hmm.
those weights in there, just the weights, nothing else,
Hmm. Hmm.
no other exposure, and then I
Hmm.
test it on the same data set. It will score
Right.
higher than the teacher.
That's crazy.
It's
Able to
it's
imagine that. Yeah.
bonkers.
Yeah, yeah, exactly. So how DeepSeek R1 contribute to democracy of AI by making deep learning more accessible and understandable?
That's a fantastic. I mean, so to me, like this is like I don't like personally, as like a from the research standpoint and as a researcher, I don't think that DeepSeek has done anything revolutionary or brought anything revolutionary to like the market, right? Like if you actually
It
understand
is
and you've
just
been like keeping
reinforcements,
up
right?
on the back end of this, yeah, this is like this is great, right? With their GRPO and all of this, but GRPO like um people have been experimenting with it on the back end for like a few months before this, which is why they say it themselves, right? Like they are like all they did to build this model. They were like, hey, what's the like the most cutting edge research? And then they very smart guys, right? And they had extra time and extra money, and they just
Right.
put it together. And then like if
Right.
you put me in that same group, GRPO is where I would go to. Like, yeah,
Ah.
sure, let's go. Like, let's do GRPO, right? And then
Right.
so they're just building off of that. And that like
Mm.
that's the part that people don't like. Where like uh, people have been talking about these things for a long time. Like DeepSeek just
Completely.
happened to be like the missile. I don't know why, but it was.
Right.
I'm glad that it happened, right? And
Completely,
that
yeah.
it's sure. Like now it's now this is a part of the public consciousness.
Completely. And there are a lot of things which will be happening just like DeepSeek, which are on the edge and which will come out on someday, right? Like on the quantum
Exactly.
computing.
I think that's exactly it. And
Right.
then now that kind of this has been come out into the ether, I see, and I am already
Mm.
seeing exactly that, right? Like more and more
Right.
discussions, like here's other edge things, and like here's where we're, like so
Yeah.
here's where we're
Right.
fully at, and we can actually like talk about like where we're at
Completely.
and cut through like kind of the hype versus the like
Right.
like hype versus what's real.
Completely, yeah. So what's this about? Is this explaining how the reinforcement function works?
Yeah,
What
this
this piece of
fantastic.
means?
Like I love this, right? So
Yeah.
when you talk about reinforcement learning, typically when you
Right.
talk about reinforcement learning, it's associated with a concept called PPO, proximal
Okay.
policy optimization.
Okay.
And then optimize, that's the reward mechanism, right? And then so
Right.
when we're talking about both of these concepts, we're talking about the reward function. And then
Hmm.
PPO is based purely off of environment. Like you need an environment in order for PPO to work. But
Okay.
so that's what they. So how you get a LM model to get that reward function is you say, hey, instead of and doing the reward function off of the environment, we're going to do it off of group relative policy. So it's instead of PPO, it's GRPO. And then so you're just changing the function of the reward function, which is complex mathematically, right? So you come up with this you essentially you first come up with the framework, like okay, I want to do this, right? You understand it, the concept. I need to have a policy, a reward policy that is not environment based because the LLM model is not environment based. So then I work out a framework, then I work out the mathematical framework, and then I build from there, right? And then you build out like GRPO itself, and then that's kind of how they come up with this concept, and how people have come up with this concept. And then this is just the mathematical framework of what goes on. Like this is how the model is rewarding itself. Is this
Oh,
complex mathematical equation?
okay. That's that's awesome. So that's what reward modeling is. So they basically make something that gives the model some kind of environment where it can reward itself. Is it like that?
That I think that's a good way to look at it, right? Like, yeah,
Mm-hmm.
so it's kind of simulating the environment, and then so
Hmm.
it's there, and as you can see here, it's based off of accuracy and then format, and then so they're giving
Ah,
it like two rewards functions in this, which is unique as well, right? Because typically you just do one reward function, and then
Right.
so they break it down to kind of like a long term and a short term reward function, which is interesting concept within this too.
So what's long and short term things?
Yeah. So like typically like let's a good example would be so with a typical reinforcement learning like Atari games is very popular, right?
Right.
And then so let's say that you're training a model on Pac-Man,
Right.
and then the model can go in any direction, like up, down, left, or right. And then
Completely. Yeah.
yeah, and then let's say that like in this instance of up, down, left, or right, where the model is, no matter which direction it goes, it's going to eat a dot. So it will get a reward
Right.
of +1 no matter which direction it goes, right? So
Right.
in that's the short term reward. But let's say
Oh,
that
okay.
if it looks at the long term reward instead of just the short term, let's say that there's a ghost 5 pixels to the left. And then so if you incorporate long-term reward into that, so short-term reward, up, down, left, or right, all +1. Long-term reward going left would be -1, and then going like right would be like +2. That'd be
That's
like the
true.
best outcome, right?
Right.
And then like maybe up or down is +1. And then so it
Hmm.
changes the shape of the reward function overall. Instead of
Right.
+1 all around, it's zero. It's like -1, +1,
Right. Right.
+1, +2.
Yeah, that's awesome. So is that how Tesla algorithm works as well? Do they use reinforcement learning as well in their self-driving cars?
In the what?
In the Tesla, like the self-driving cars?
Oh, and yeah. So with like absolutely like the with self-driving like reinforcement learning is like a huge within like simulation training for all of
Right.
these. So like when it comes to like self-driving cars, things like that, like that's where those types of applications are where like this started, right? Like that's kind of like
Right.
the
Yeah.
first like we need that to be the base, and then
Completely.
now we're like
Completely.
expanding upon it. Like for a while it was like so reinforcement learning like good examples like you brought up like self-driving cars, things like that, right? And then you have
Hmm.
an explosion of LLM models which
Right.
they came about via just pure data like kind
Yeah,
of like just
exactly.
shoving
Yeah.
data in there, right? And then so it's
Right.
like people for a while they differentiated the two, like, and it was a question like could you do reinforcement learning for an LLM model? How would you do it? What would it look like? And then like
Right.
that was a question for a long time, like up until like a few months ago. And then so
Yeah,
like
so yeah.
we're just now exploring it more, and then
Right.
it turns out like it's actually a far better method than what we're doing.
Right. That is completely awesome. So let's go ahead and explore some of these. Now, we'll go through these papers one by one. So let's dive into this one. So, what's exactly like distillation of knowledge in neural network?
Yeah, this is an amazing paper, right? So this is put out by Jeffrey Hinton. So just highlighting that
Right,
up front. And this is a Google paper. So like pre 2017, all of
right,
these are going to be Google papers, right? Like like
right.
I mean all of them,
Yeah, most of them. Yeah.
a big amount of this research is like from like 2000 to 2017 is coming out from Google. And then
Right.
so this Hinton paper is very specifically on that concept of that like that student teacher and how that works. We
Hmm.
like knew all of that coming in to all of this because of this Hinton paper, right? Like
Right,
that you could actually do this, that knowledge distillation is a thing, and that you could transfer like the weights and do that to smaller models. Like I remember there was a period with like when the llama model first came out, right? That's where the open source community first started diving into
exactly. Yeah.
knowledge distillation, and this paper
Right.
like came up big during that
Big.
time, right? Because it's
Yeah.
like people realize like oh like we you can do knowledge distillation on the llama model, and then so that's where that's how they came out with the vicuna. And then like for a while the llama model was like fine-tuning llama 1, and then they came out with llama 2, and it kind of went from there. But for a while it was all based purely off of this distillation paper where people were running off of.
So what are like MNIST? What experiments they were like looking up to?
Yeah. So fashion MNIST is like when it comes to a machine learning, like this will be like this is like kind of your based test, like fashion MNIST is like your most common test, right? Like, so if like how well does it do on fashion MNIST, like then that's kind of like I can use that as a good benchmark. And then very straightforward, it's exactly what you would think, right? So it's images, and then it's broken up into 10 categories, and then so it's like shoes, pants, shirts, blouses, it's fashion, right? Fashion MNIST, and it's like just different examples. So like pants, there's just one. Like jeans, there's just one example of jeans. But like
Okay.
shoes, there's like multiple examples. Purses, there's like multiple examples. And then you train a model on that, right? And then it's how well it's able to do on fashion MNIST is kind of just like the standard benchmark. And then like uh, your typical like performance on it, like HTC models or like a good small fine-tuned model will score around like 80 in the 80 to 90 percentile on fashion MNIST. So it gives you like good benchmark, right? If your
So,
model's up front scoring like near 100% on fashion MNIST, like you've got something good. Like,
so what exactly is passion English? Is that a data set or something else?
oh yeah, yeah. So, what exactly is the MNIST portion of that? Like that's a good question. Like I believe so. I believe that the MNIST portion is related to like the like like the research institution.
Okay.
So I like I don't want to say the wrong institution,
Okay,
but I
okay,
believe
okay.
it's
Yeah,
related
yeah.
to the
Yeah.
research
All right, yeah.
institution.
So, when they mention specialist models, what they're trying to say, so they developed some models who can like which can do some specific task really well.
Yeah.
Is that
So
the thing?
that, that's a fantastic question. Like so. Like this is an important concept when it comes to distillation and student teacher models overall and things like that. I'm glad that you bring this up, right? So um, this whole concept of distillation, so generally speaking, what we're doing is we're taking like a bigger model and then
Mm-hmm.
we're distilling that information and that knowledge into a smaller model, right? Like so let's say our teacher is 7 billion parameters. We distill it into a specialist model which would be 1 billion parameters. And then prior to that, like that distillation, let's say that we we want a specialist that knows coding very well, right? Like Python. So
Yeah.
I would fine tune the teacher on Python, right? Like I want it to know Python very well, and then so I fine tune that model, and then I take those updated weights from that fine tuning because it's fine tuning on Python, and then I take that and then I distill that, and then I put that into the 1B model, and then that 1B model is now a specialist model when it comes to Python coding. Like it will score better than the teacher when it comes to Python coding. Anything else is going to score way worse. Right? Even like C++ coding, it would probably score worse. But like
Oh, okay.
Python coding specifically, it's a specialist and it will outperform its model class and its size based off of on Python coding specifically.
Right. So what this function is about, like performing in inference within symbols of specialists. So they're doing some things with these specialist models now.
Yeah. So this is, I mean, this is like this particular equation that you're pointing out here. It's an interesting
Right.
equation, right? So
Right.
this equation within this paper, it very essentially is sorting out and showing like how the model essentially breaks up and breaks down this information. Fashion
Okay.
MNIST is a good example of this, right? Because so
Right.
fashion MNIST is broken up in the human sense into 10 categories. Like
Mm-hmm.
if I categorize, and it's again like pants, shoes, shirts, etc., blah blah blah, right?
Mm.
But
Right.
for models, AI models, they are classifying objects like off of shape and then categorization of shape, right?
Mhm.
So fashion MNIST to a human is let's say 10 classes, but fashion MNIST to an AI model, let's say it's 36 classes. And
It's
when you
awesome.
actually like break it out, right? And you actually
Right.
understand it, because and so classes is really what you think of it, right? Like so
Mhm.
the it's the model organizing the information, and that's what it does. Like when it takes in a data set, that's what it will do, right? It will take in that data set and it will classify it and it'll break it down into classes, and that's what it's learning and training itself on, basically.
So what are the targets in this this context, soft targets as regularizers.
Yeah, so regularization function it's like that's a good question, right? So when you come into like a kind of like regularization and adding like a dropout within this, essentially like you're adding noise. Is kind of like the bottom line, right? Like and noise is interesting within this, right? Like you would think like in a lot of instances like noise would be kind of bad, but so within like the the reward function that we're utilizing, that we're training towards within when this paper came out especially is gradient descent, right? And then so gradient descent is like it's like kind of that loop like this, but the problem is that you can have local minimas within gradient descent, which means
Yeah.
that like it might think that it found the bottom, but it's
Mm-hmm.
just like in like a little divot, like a little pit, and but there's like a chasm right next to it.
Yeah.
And then but so it'll find like the divot, and it'll be like, hey, I found it. Like I'm in a
Okay.
hole, like I'm not gonna get out of the hole. Like
Okay.
and then so
Right.
you're just like, here's a little bit of noise, like get out of the hole. And it's
Mm.
like, oh, there's okay, here's the chasm.
There
Like,
is a
okay.
chasm, right? So it can find out the chasm, right? Like once
Yeah,
it knows, yeah,
exactly. Like
yeah,
yeah, it helps the model explore better. Like it kind of
right.
counterintuitively.
That is awesome. So that this thing existed since like 2015. Like thinking that it is like really awesome, man. Like
Yeah.
I used to think all these things came around like only 2 3 years ago, and when I look at these papers, all things were just there, and just the like things were just developing, and just something came up from that, and that was
That I mean,
the
like
like something.
that's the interesting part of the history to this of me, right?
Yeah.
Like, so I'm glad you bring this up to me. Like, so one of my like idols within this is
Mhm.
Richard Hamming, right? Like so
Right. Yeah.
like Hamming, like if you check out Richard Hamming, like so he was part of Bell Labs.
Mhm.
He's in World War II he was a code decipherer, and
Mm.
then Bell Labs and early IBM, Hamming distance. There's a lot of like famous parts of early machine learning that
Right.
are
Yeah. I think I read his paper or something. Did
yeah
he write any paper?
he's cited in lots of papers
Right. Yeah.
overall, like etc. And I mean he's like his era was World War II. Like
Mhm.
and it literally goes back to that far, right? And it's people had these ideas and these concepts for long
For
times.
a
It's
long
just
time.
compute like and like I don't like a big thing within this. Like people don't understand the big breakthrough that we had in the early 2000s with parallelization of hardware, right? Like a lot of this, like why we are here, it's all because of like GPUs, and we're talking about like GPUs, and it's all important and all of this, right? We wouldn't have GPUs as we know them now, and this whole track if we didn't have parallelization of hardware in the early 2000s. And then like so before then like computers just worked differently, right? It was like different hardware, and so I could
Completely. Yeah.
conceptualize this. Like swarm algorithms is a fantastic example, right? Like because swarm
Right.
algorithms, like people were thinking of it in the '90s, and then they were like you. There's papers from the 1990s, but like it didn't work, and it was flat out like
Right.
we didn't have the technology. Like it just didn't
Yeah.
technologically work. But
Mm.
now it's just like yeah, it works, and you just plug it into a GPU, and it's amazing.
It's
It's
amazing.
awesome.
Yeah. Like it makes your whole thing work really faster than CPU. So that's awesome. So
Yeah.
yeah. So the word expert, which we see here, is that similar to what we notice as agent in these days?
Yeah. So like that's a good question. Like to me, like agents and experts are starting to become interchangeable. So like what we refer to like the specialist, that's like an expert would be like a specialist in this instance, right? And then so what this model utilizes and this expert architecture utilizes is kind of that architecture that I just described, right? Let's and but you don't have to. And when they're dealing with mixture of experts models, they don't distill to a smaller model. They'll take like let's say like a 7 billion parameter model or a 14 billion parameter model, and then they'll train it to be an expert, like so a math expert or a coding expert, philosophy, etc. Right,
Right.
like one
Yeah. Yeah.
individualized subject, and
Right.
then you create the model overall by combining like multiple like 8 experts or 16 experts together, and then you part like the output, like how you structure the model overall and you build the model, is to essentially like infer when it should call each individual expert depending on like the prompt and the scenario, etc.
So this is the question which I'm having like just right now, and it is like completely maybe out of this paper, scope of paper, but yeah, hear me out. So I was thinking if the model, when we visualize model, it is just a geometrical shape of the data of all kind of data which is placed in the vector space in all different places, right? So if that is the case, then if we think as like universe as the just as a data, then there should be some kind of like some kind of thing where all the data, all the knowledge there possibly can be, or all whatever the thing which universe operates runs on, like the basic physics or anything, that should be something there should be some way to decipher that all that into the through like vector space and make scientific breakthroughs, learn about the whole universe through what we have as large language models or something. Is that making sense?
What you just said makes too much sense, actually.
Ah,
Um,
okay.
so uh,
Yeah.
I would uh, you would probably utilize HDC framework for what
Mhm.
you just laid out, and then
Mhm.
I have a bunch of like NDAs that I can't say anything more than that. But
Right.
like what you just said is probably true. You could probably
Oh,
do that.
yeah. So that will be like crazy thing. Because I just got that imagination. Like, if everything is like, if we think just in the terms of energy and data, then why not that cannot be possible? And if that is
Why not?
possible, then there are like literally limitless things that humanity can achieve. Literally,
The
we
math
can,
checks out, right?
yeah,
It's a simple correlation. Like if you understand, like you start piecing together how this works, and then you
exactly,
come to that realization. There's the
yeah,
realization that that equation exists, or that
exactly,
equation has a probability of existing, right? Like, and it's just a
exactly.
matter of finding. I don't think you're wrong.
Exactly. Even like we even get to see time machine or something in some like upcoming 50 years or something if that happens.
Yep.
Because we just it is just a matter of scientific innovation and the more things that we know about the universe. That's all about
It's
it, right?
it's
Like
exactly it. I
all
don't, you're on the right track 100%.
nice. So let's go on with this paper now. So deep neural networks are easily fooled. So what this like these authors are trying to say, like how deep neural networks can be easily fooled.
Yeah. So this is like interesting paper here, right? So this
Right.
particular paper is dealing specifically with like kind of image classification, and then like how models like are like how the modality of data influences kind of the shape overall of data. So like this goes overall into topology. And topology is an interesting area, right? Like topology is an interesting area of mathematics, which like topology like comes about and starts from like the 1600s, right? Like Poincaré, I think. And so like he's like debating with like Descartes about these things, and comes up with these concepts, and then it ties into calculus uh, as to kind of like the mathematics behind this, and the thinking and the logic behind it. But then it doesn't get picked up for a long time, and in current math, like we're like it's where we're at because we have kind of like underexplored this area a lot. But so what this paper and what a lot of papers show is that every piece of data has a shape to it, and then within this particular instance, we can essentially just modify and kind of utilize shapes of data to um, fool the models and to like kind of like
That
trick
really
them, right?
makes
Like
sense.
you
Right.
utilize, you can
Okay.
utilize shape like to like code almost, right?
Right,
And then so
right,
by
right.
right shapes, you can like do different types of like adversarial attacks.
Okay. So, like, am I explaining this right? Tell me. So, this is what similar to say of image of like the data of image of cheetah. This is the similar thing to that, and it is not true. And that's why like the DNN is getting fooled by this image, and it is thinking that is cheetah.
Yeah, that's exactly it. Yeah, yeah.
Oh,
Exactly like so.
that's awesome.
It's good examples were I've seen examples of like a cat and a cat will be behind a gate and then it
Hmm.
will put stripes onto the cat and it'll be like, well, it's a
Hmm.
zebra or something like like
Ah,
something crazy will come out of that, right? And it's like
okay.
it's all boils down to patterns and pattern recognition, right? Because like the bottom
Right.
line is so uh it's the same way that your brain works in certain areas, but like this is far less complex than how your brain. Like your brain is
Completely,
the
yeah.
ultimate like camera that has ever been invented, right? Like
Completely, yeah.
there's no better camera than your eye, and that's
Completely.
and how it processes and is connected to the brain. This is
Right.
doing like what that same process, but like
Hmm.
infinitely less good.
Yeah,
Like
yeah, yeah.
I mean, it's just
Completely,
like
yeah.
it's just not nearly as good.
Right.
And then, but so what you're doing is you take in an image. Let's say in this example, we're looking at an image of a guitar and a penguin, and then
Mm-hmm.
we convert that image into a different signal, right? Like so, we're
Hmm.
converting it into in this instance, we convert it into like binary or noise or whatever like whatever we convert it into, and then electricity in our brains, and then that's what gets passed in, right? And then so you're essentially just like in the instance of the guitar and the penguin, it's not passing in a guitar and a penguin. It's passing in the binary of them, right? And then so depending on how you are processing that, and if you process it the wrong way, it could fuse them wrong. So it could fuse that guitar and that penguin very easily, right? Or like different types of scenarios, like and that's kind of like where you can run into like different complications. It's kind of like how
Yes.
they illustrated out here, right? Like this is exactly what's
Uh,
happening in that
so
illustration.
if that's the case, then when we generate images, do we have these things as well? Like whether we are prompting something unusual, like generate flying penguin or something, then it will give me some weird shapes.
Like I mean like I don't like so
Mhm.
the I mean I guess the human equivalent to this to me would be like so I guess like an example that I like to think of most commonly is so, like your like our nose is like directly in front of our like our eyes, right? Like so
Eyes,
like
right.
your nose should block your vision like it like but it
Uh,
doesn't block your
yeah, it
vision.
doesn't block our vision.
Yeah,
Yeah.
yeah. It never because you're like your mind is like predicting that your nose is there and it's removing it, right? So
Right.
like that it's so you're never actually like processing like the real environment. And that's like you're processing the prediction, and like that's the same thing that these models are doing. It's processing it's not processing the picture of the penguin. It's processing the prediction of the picture of the penguin, and then so the prediction of the picture of the penguin could be just how it's shaped, like very close to the prediction of the shape of the guitar. And like you wouldn't know until you actually do it.
So, what is ImageNet? Is that a model, different model as well?
Yeah, ImageNet. Yeah, yeah. So
Okay.
ImageNet is it's a pre-trained DNN. So like
Hmm.
very specifically, like it's a pre-trained model for like training like images. Like if you so you don't want to
Hmm.
start with scratch, like you don't want to like have a cold model, you can utilize ImageNet. Like yeah, it's just a
It
research
is
tool,
open
really
source.
awesome research tool for DNNs.
That's awesome, man. All these open source things are really awesome.
It's
So,
amazing. Yeah, it's the
yeah.
best.
So what we understand from like training MNIST deep neural networks with pooling images, like what they're trying to say here. N plus one class same number of images as other MNIST classes. Hmm.
Yeah, like essentially like what it's saying is that like it's it's what happens within this is counterintuitive, right? So it means that like if you train the model on like adversarial examples, it doesn't like there's no generalization that occurs within it, like not as much as you would think, right? And then so it's here's a good example. Like I mean, here's perfect, right? So they fashion MNIST in the data set that we're looking at here is broken up into different classes, like I said, right? So 10 classes, 0 through 9. And then, so let's say that I train a model on adversarial attacks on that first row, so 1, 9. And then like I give it like false data. And then it's and then I get it to like start predicting very good classes 1, 9, right? And then so it's like 99% accuracy after my training, but then all of a sudden class 1, 8, it won't, like it doesn't change. Like and the accuracy of class 1, 8 could actually be worse after fine tuning. So like it could, let's say like, and just how it works out, like it doesn't transfer or generalize like you think it would, and I don't know why. Like that's still like an open question.
Completely, yeah. So that is what they have written where when they say producing pooling images via gradient ascent. So this is
Yeah.
different. Gradient, what is gradient ascent?
Yeah.
Normally, all everyone
This
know
is
gradient
super
descent.
interesting, right? Like I
Yeah,
like so gradient descent is again like it's that slope,
it's
right? Like
going
that
down the slope, right? So
yeah,
we
yeah, yeah,
climb
and
the
then like
slope now.
the bottom of it, and then
Right,
like that's generally that's how we train reward models off of that reward,
right,
right?
right,
And then
right, right.
so essentially you just take that reward and then you're just doing the opposite. Like it's amazing to me that things like this work, right? You're just saying
Yeah.
like okay, like we trained you on a bunch of images, take
Hmm.
the reward that we trained you on and then do the opposite of the reward, and then like
That's
that, and then
that's
you spit it,
awesome.
you get an image out of that, and then you
And
can,
that
and then the
works.
image is the uh, refractal opposite of the other image. Like kind of
Right.
crazy, right? Like
Right. Can we think at is like a back propagation? No, right? Because gradient
oh yeah,
descent
yeah.
itself
So you
has
can
a back
absolutely
propagation.
utilize back propagation in this. Like, so back propagation can be utilized in this instance as long as you know the error, right? So that's kind of like
Right.
that's the usefulness and the unusefulness of back propagation. Like why doesn't the human brain utilize back propagation? Because like in a real world situation, like I don't like you almost never know like what the actual error was, right? Like if you make a mistake, like you never know like exactly the mistake that you made, like you, and so you can't backpropagate that. And then so backpropagation is great, but the limitation is that you have to know like that exact error to backpropagate over. So if you do, then it's great. If you don't, then like, it's it's not useful at
Yeah,
all.
maybe this image is explaining what you were talking about, like training set, test set, adversarial example, these things, right? Then
Yep, exactly. Yeah,
evolved
and then yeah,
images.
exactly, and it's showing that like essentially, based off of the different classes, you train it off of adversarial examples on different classes. You would think it would
Right,
have some sort of impact on other training on other classes, whereas it doesn't, right? Because it's just
right,
off of the categories, right? So it's just it's
right.
um, you have no direct correlation, but then this is also showing too that gradient ascent method, which is super cool,
Gradient
right? Like
descent, yeah,
that
that was something
script
different
encoding,
which
yeah,
I learned today. Yeah, that was awesome though. I
yeah.
never thought gradient ascent would be something there. I only knew that the gradient descent is the thing. That is
Yeah,
really
exactly.
awesome.
Yeah, it's kind of trivial. Yeah, it's pretty cool.
Yeah, yeah, pretty cool. Yeah. So that's really awesome. So that's the second paper. Let's go through this one now. So how transferable features in deep learning how transferable are features in deep neural networks?
Yep.
Okay. So what do they mean by this title?
Yeah. So like, very. I mean, it's. I mean, very specific. Like, it's what they mean within this is like the like how transferable is like the actual like learning and the data itself, right? Like so within this it's very transferable when we're talking about the weights, but then not transferable like outside of that, right? Like it's kind of like how uh we're learning within this, right? And but what we learn within this is like what I've learned from this, and what I learn more and more, and relating it to this paper specifically, is that um, this question is it's like kind of like an oxymoron, right? Because it's they're not very transferable, but if you train
Exactly.
a model on them, then they're the most transferable thing on the world. Like there's nothing more transferable. So it's kind of interesting, right? Like up
Yeah.
front, they're not transferable, but if you're talking about just like you fine tune it and in its distillation, you can transfer whatever.
So with this, I got to like I remember one LinkedIn post which was saying that DeepSeek bought the premium version of ChatGPT and they made it learn through the reinforcement learning whatever the things are in there in ChatGPT, whatever responses ChatGPT gives. So is that is that what they did or something? Or is that what this thing means as well, transferable features in deep neural network,
The,
or
uh,
it is only biases,
Yeah, yeah.
transfer
So
bias.
what you brought up
Right.
is a good example of like so what they're like generally what they're referring to in this particular paper is like
Right.
they examine it more off of like the different layers and breaking it down off of like that way like but
Right.
the
Okay.
method
That's
that
it.
you
Okay.
just brought up is a fancy like that's definitely relatable to this and
Ah.
then
Okay.
so what we're finding more like we're still in the infancy of this particular subject all around, right? Like
Right.
can like how linear can we make an LLM model's inputs and outputs? Like, because LLM models,
Right.
like we're dealing with like huge like billions of parameters, billions of
Right.
algorithms, etc. So it makes it
Right.
hard
Right.
to
Right.
trace back that
So,
linearity, which is what this comes back to, right? So if we could
so one
fully
more
trace back to
question. If,
linearity, then we can do the reverse, right? So if we understand
Mhm.
how it works, then we can just transfer that to another model, like how it works,
Right.
and then
Exactly.
another model would then do it.
Right.
And then so uh, all of that kind of just funnels directly into this question overall.
Right. So if that's possible, then will this be possible in future? Like we're watching modules are teaching other modules and they're getting better. Like a lot of things they're special into. Like one module is special into physics, one module is special into some literature, and those two are teaching themselves and making some other module who is uh, philosophical physics model now. And something like that. So will that be something that we are going to see in the future?
I mean so that particular instance is like what like when people talk about like the singularity that's what they refer
Right.
to, right? Is that
Right.
like the singularity is like self-improving AI
Right.
where it can iterate itself fully without human involvement. Uh,
Right.
we're like 80% there, I'd say
Edgy.
currently.
Wow.
Like the model still requires human prompting, right?
Right.
And human in the loop. And then what we can see is like agents are like
Mm-hmm.
if to me, I think that personally that this question is directly correlated to agents. If we can solve agents, we solve this problem. Uh,
Right.
we haven't solved agents, right? Like I saw recently, like today, there's a new like benchmark test that came out, and it's we're about like 60% or so when it comes to agents, right? Say like call it 60% out of 100. And then so we still got like that 40% to go. So we still have a ways to go and problems to solve within this equation. And then like I think a lot of people take it for granted that we will solve those problems, right? But these problems that we have here, going back to what you said earlier, like this isn't none of this is new, right? Like, and then
Yeah.
so these exact problems aren't new either. Like people thought that they were going to surpass this problem in the 50s and the 60s, and they didn't. So like, what is different today with regards towards this exact problem? I don't know. I don't know what is different. There's a chance that we might not solve this problem. Like I think people should be prepared for that.
Right. Yeah. Like anything can happen and anything can like maybe take a lot of time. Who knows?
Yeah.
Yeah, that might be the thing. So is this the diagram which explains how the features are transferring between two models? Overview of experimental
Yeah, that's
treatments and
exactly what's going.
control.
Yeah. So it's
Okay.
weight transfer, and then so this is exactly what I mentioned, right? So it's all just weight transfer. So you have like weight A1, weight A2, weight A3, weight A4, right? And then so you
Hmm.
just transfer that, you just distill that. So weight A1 becomes weight B1, and then so let's say that weight A1 is 0.09, then weight B1 becomes 0.09, and then weight A2 is 0.50, weight B2 becomes 0.50, and then yeah, you can literally transfer and distill knowledge via that method, like just by uh, distilling the weights. And then you can also too, like you can be selective with that distillation, as long as so let's say that for Python coding very specifically that um, weights B1 through B3 are like, that's for Python, right? And then like B4, B5, B6, that'd be for like C++. So let's ignore those. And then so we can just distill straight B1 through B3 and then nothing else, and then just take the Python information.
That's super cool. This
Yeah.
thing, like knowing that this thing existed before like 2018, even this paper came around something like 15 maybe. And that's crazy. Like that's amazing to imagine. So we had all these things from a long time.
Exactly. Yeah, no, like we've had this like individualized knowledge of all these concepts for a long time. And it's hard to put it all together, right?
Right.
It's just so many different disciplines and putting it all together. I think that's the
Completely.
hardest part.
Right. So what's this diagram is telling us? Transfer plus fine tuning improves generalization
Yeah.
performance
So
rewards.
this is interesting, right?
Mhm.
And this is essentially like fascinating study to me, which is showing that like your best method overall is transfer learning plus fine tuning, right?
Hmm.
Like that knowledge distillation plus that fine tuning gives you kind of
Oh,
like the best performance overall, and that
okay.
you can utilize like that those methods and utilize fine tuning to overcome like performance gaps, things like that. But then it's also showing that you can uh, overtune, like you start to get performance uh, overfitting, and then you get significant decreases in performance with overfitting, and then via no matter which method that you use.
So is overfitting good way to go or it's not? What do you
Uh,
think about that?
Overfitting is interesting, right? So I
Right.
mean, uh, I know people that are like kind of like on the cutting edge of this.
Hmm.
Like
Hmm.
they experiment like with overfitting a lot, and they'll do like
Hmm.
some crazy experiments, right? Where it's like
Right.
if you overfit on a data set, and it's called like grokking, where like
Right.
you'll overfit, but like you'll overfit for like 1,000 epochs, like kind of like overfit forever, right? And then
Right.
like
Right.
you'll note like a pattern will emerge, like for like 500 epochs, it just won't do anything. It'll just, but then all of a sudden, you'll just see like out of nowhere, like this random, like emergent gain will come from overfitting for long periods of time. So there can be benefit within it, right? Uh, nothing should be off the table when it comes to exploration of these things. That's how I look at it. And that's where these breakthroughs come from. Is like, uh, people coming at it with a more open mind, like not coming at it like, oh, you can't do that because people say that you can't do that. Like, well, no, like
Anything is
just do it.
possible. That's what I learned. All I learned from all the research
Yeah.
things I'm going through. Because whenever I read any research paper, and sometimes like I come across something that's like something which I thought that will never be possible, and that's there. So that's like a eureka moment for me, and that has been
That's why I
happening
love
quite
AI
lately.
overall, right? That's, I mean, like
Yeah,
those are my favorite days, where it's like I
yeah,
woke up today and I was like, I would never think, like, if you asked me in the morning, like, could you do
yeah.
this? I'd be like, no, you could never do that. And as I think
Exactly.
I
Yeah.
find, whoa, this is possible. That's crazy.
That's crazy. Yeah. So what's this diagram is this man-made natural split and random unthread filters and network is chopped and retained. Relative top one accuracy. Higher is better.
So I'm assuming, like, so that man-made versus natural split, I'm assuming that
Mhm.
that's what is like going into kind of like it, because this is measuring classes, right? I think I'm assuming it's going into kind of what I was talking about before, that like
Right.
what we recognize as a class is, like, generally speaking, like not what an AI model is going to recognize as a class, right? Like what, like fashion
Right.
MNIST, like um
Right.
it, like we group sneakers together, but like maybe there's, I don't know, like there's a some sneakers have less shoelaces than others, or like some have a different shoe. Like there's different there's some pattern that makes you actually have like 2 or 3 different types of sneakers as opposed to just one sneaker.
So I know just the concept of normal weight, but what's the random weight?
Yeah. So random weights is interesting, right? So like with
Right.
untrained with an untrained model, like you have to like no matter what, like you never like you're never setting the weights to like 0.0 to start, right? Like the models needs something like it's like I mean honestly like how I boil it down to is so the models are building shapes, right? And then like they're building shapes within digital space, and then they're building shapes off of this data set, and then they're taking a data set, but like they need a starting point, a starting point within their digital space, and then so that's what you do. Like when you're randomizing the weights, you're just saying like, here's your starting place, and it doesn't really matter where the starting place is. It's just like for measurement purposes, you need a starting place. And then so it's just here's your starting place so you can measure from it. And that's what it does.
Yeah, that's where the like classical thing came. Like if we have only zeros as starting places, then it will not work really well.
Exactly.
So
Yeah.
that's why
It needs
we
something.
randomize
Yeah.
that.
Zero isn't a starting place. Like it needs to be
Right.
something.
Something.
It doesn't
Okay.
matter what it is. Like you can
Right.
be completely random numbers, but it
Right.
needs just you need the numbers.
And it should not be too much of big of a number, right? As well, like it should be a bit like some decimal, like 0.1, 0.000, something.
Yeah, and there's a like so that is like this area is very very underexplored within it.
Right.
Right, everyone just does randomization within this because
Right.
it just works, right? Just randomize, but uh
Hmm.
like are there patterns, and am I aware that there's patterns like that, like what you just described, that are within this? Yes, but like no one has like it's very underexplored. Like um do you maybe like what if I start with lower random weights as opposed to higher, etc. Like that. I mean, those are fantastic questions. You made me think a lot of, yeah, like that's an underexplored area, but my hypothesis is very strongly that like you are very much on the right track with that.
Yeah, that was all about this paper. Let's go on the this one now. So CNN features off the shelf. Okay, astounding baseline for recognition. Hmm.
Yeah.
So
CNN models are very interesting overall. So this
right.
paper is essentially talking about like convolutional neural networks, and then so
Okay.
essentially convolutional neural networks are doing a convolutional loop, right? And so CNNs are very specifically for image based and image trained models, and then so this is kind of just like and we like for images now, like this is the main primary model that we use is CNNs, and then so this paper is just introducing that architecture. And then it's just so CNN, it's just the type of revolution that it's doing, right? So it's doing a convolutional involution as opposed to like an RNN, which is doing like a reverse involution, etc.
So what is convolution in compared to our uh, uh,
Yeah. That's a good question.
reinforcement
So I'm
learning? Yeah.
assuming that they'll do. I assume in this paper, I think that they have. Oh, here we have it here. So
Okay.
essentially, the convolutional loop is this, right? So it
Hmm.
starts off with the image, and then
Right.
you have your annotations, and then you're
Right.
essentially reshaping the image, shrinking the image, learning
Right.
those kind of shapes, extracting
Hmm.
those specific features, and
Right.
then that's your feature extraction there, and
Hmm.
then you do that same loop. Like it's a convolutional loop back to the end.
Mm.
Like it's so circular process.
Circular
Yeah,
process.
convolutional
Okay.
through.
And it gets better and better with each loop.
Exactly.
But
Yeah.
I,
Each loop is like it's able to it like all of
Mhm.
these models. It's always either prediction or classification, right? So then in this instance,
Right.
it's prediction. It's prediction and class. It gets better
Mhm.
at predicting the classification.
Right. So what's support vector machine doing here when we have all these things here?
Yeah. So like the support vector machines is kind of like the end output result, and then so that's
Hmm.
the like it's translating the image into vectors, and then
Wow.
that vectorization. So remember like the analogy that I gave where the human eye doesn't like you're not actually seeing the image. It's translated to electricity first and then going through.
So is it
Like
like kind of? It's not like kind of softmax function, right?
yeah, no, it's more like this is the like it's the translating mechanism, and
Translating.
then a
Okay.
support vector machine is just translating it into
Okay.
like electricity.
I'm getting intuition of it now. That is really awesome. So it is kind of similar to a reinforcement learning, but it is not, and that is awesome. That
Yeah,
is
I never
crazy.
actually thought about it from like that, but yeah, like yes, I can very much see how you can draw that
Right.
conclusion. It's very similar, yeah,
Yeah.
like yeah, because your PPO is involved in this, so yeah, you're like
Right.
you very strong inclination that yeah, you're good on the right track.
Yeah. This is really awesome, man. So, okay. What are these people saying? These are some conversation about something. Is that a model which is talking about? Will okay.
Yeah, this is like there was a question of like would deep learning actually work for images, right? And this is like that's the
Right.
whole question. Like so at this paper and what this paper proved it like and it's a foundational paper in that concept is that like
Right.
kind of like modal and what we are our understanding of this now is that like modality is like not totally important. Like whether or not like an image, whether it's an image or a video or audio versus text, like we can just convert it all to binary, right? Like and
Yeah,
then like
that's the
like
really crazy part. Yeah.
yeah.
And we can have the image, sorry, save of the whatever data we put in, and that will be like understandable to that network, and
Exactly.
everything will
Yeah.
work.
It's just all systems of representation, right? Like an image is a system of representation, a video, etc. And then so you just
Right.
convert one system of representation to another, and as long as you have like a linear process for that conversion, and you know how to do the calculation to do it, that's all you need.
Right. So Pascal VOC object classification is some way to classify images, or uh, that's something that these like research group did.
That's all. Yeah, Pascal math. It's just like the
Oh,
mathematical approach to
classify
classifying
images.
images, and then I
Oh,
think the
okay.
data set as well.
Okay, that's really awesome. So is this equation the like explaining the same thing, Pascal mathematical way to classify images?
That's a so that's an equation for an SV for a support vector machine. Like that's
Mm.
like the actual equation for the SVM itself. That's a pretty cool
So the
equation. Like
basic
so yeah,
equation
that's
for
calculus.
SVM is this. Okay. All right. So can we dive deep into what this equation means?
Uh, For sure. So it's essentially it's like so it's doing like going through and then classifying the label
Mhm.
going through I like I don't know what the variables stand for within this instance. I don't have the key. I would need to see
Okay.
section 3.6 to know what W C Y and WT stand for in this instance.
Should I go there? Let's see. 3.6. 3.6. Did I miss that? No. Should be here. Okay, yeah. We have 3.6 section.
There we go. So this would be the explanation of that equation.
Okay.
We've used pre-computed linear kernels for the CNN. Data augmentation is done by making 16 representations for each sample. Original image. So the cropping is done such that the sub window contains 4/9 of the original image area from the four corners and the center. So that's the math that it's doing there. We noted that the following phenomenon at the test time we take multiple all the
That is
responses.
awesome. That is awesome. Even knowing this is simple thing, understanding is really awesome, man.
For sure. Yeah, I know.
Yeah. Like support vector machine. What simpler thing can be there? But yeah, it is awesome.
Yeah, for sure.
So what is actual search method?
Facial search. Let's see. Oh, so like essentially like within this you like so within an image like it's all like it's CNN is it's classifying the image right into categories and then so it's you like essentially how it's doing that is it's searching the image flat out, like right. So like it's taking the image and then it's creating a shape, and then it's searching that shape, and then it's finding different characteristics of that shape, like different patterns, right? Like here's a connection, and then that's like so. Why does it improve off of involutions? Like each involution is because it finds more connections, right? Like it finds like stronger connections, or perhaps like connections that it didn't find via its first pass because this connection is related to that connection, etc. Right? And then like that line, and then so you like need to know like the bottom of the line in order to know and progress more up towards the top, right? And then so there's different search methods that you can use within that, and so spatial search is just essentially searching the like the full entire search space, like like treating it like you mentioned earlier, like a universe, like the data as a
So
universe is a search space.
okay.
Like I like a lot of algorithms work that way. Like they treat the search space as an actual universe. Search the universe.
That is really a really awesome way to look at it, man. Like that makes like that connects a lot of dots in my mind. So that is
For sure.
really awesome. So let's go with other paper now. So learning and transferring mid-level image representation using convolutional neural networks. So we know what convolutional neural networks are now. So what
uh,
representation mean?
Man, this is a cool one, but I have a hard. Do you mind if we go over this one next week?
For sure, for sure, for sure. We'll go over these three papers next week. Thank you so
Awesome.
much for your time and always like you share knowledge, which is really makes me and our audience learn a lot, man. And I'm really truly grateful for all that you share. And
Absolutely.
you do like all the work you do, all the knowledge you have. It is really work of really like the complex things that you learn. That is really something that I admire. So thank you so much and keep doing your work. It is really awesome, man. So thank you. Yeah, yeah. So let's make it meet in next week. Thank you so much. All right, bye.